Hello, we went through a problem with the two spheres where the dimension of both the spheres were identical. Now let us go through a problem where you have two non-identical spheres. So this particular sphere is of 20 mm diameter and this particular sphere is of 30 mm diameter. So both the spheres are non-identical. In the previous problem, we went through a case where you had two identical spheres. Here you have two non-identical spheres. So these two non-identical spheres are being placed in a trough, and the opening of trough is given as 90 mm. The total opening of trough is given as 90 mm. So this is all about the problem, and you're supposed to find the reaction offered by the contact surfaces about all of these contact points P, Q, R, and S. This is what you're supposed to find. Reaction offered by the surface will always be normal reaction. You know how to mark normal reaction. It comes in the steps. It's one of the steps to draw the free body diagram. So this is the fifth problem in your notes. So you are supposed to find the reaction offered by all the contact surfaces about all the contact points. Problem remains same as that of the previous one. I mean, the unknowns are same, but the condition is different. Even in the previous problem, you were supposed to find the reaction offered by all the contact surfaces about the contact points. But there the spheres were identical. Here the spheres are not identical. It's non-identical. This is the difference. Now, there are only two steps. The first step is to draw the free body diagram, and second step is to study the free body diagram or to go through the free body diagram. If the free body diagram has three forces, apply Lamin's theorem to find the unknown force. If it has more than three forces, go with the conditions of equilibrium. Steps will remain same. We just have two simple steps. Step number one is to draw the free body diagram. So let us draw the free body diagram. Again, to draw free body diagram, we have multiple steps. We have 5 more steps. So let us draw the free body diagram. So step number one to draw the free body diagram is to identify the center of the given objects. Here you have two objects, and again you will get two free body diagrams as that of the previous problem. Again you will get two free body diagrams as that of the previous problem. Now let us draw the free body diagram. Before that, the self weight of both the spheres are given already in the question. Self weight of the lower sphere is given as 100 newtons. And self weight of the upper sphere is given as 300 newtons. It's already given 300 newtons. Now, step number one is to identify the center. Let us consider the lower sphere as well as upper sphere simultaneously. Let us consider the center and let us draw the coordinates. Let this be the y-axis, and let this be the x-axis for the lower sphere. And let this be y-axis and x-axis from the upper sphere. Step number one is Step number two is to mark the self weight. Self weight is already given. Self weight will always move vertically downwards. So it's already given here. This is the self weight. Self weight is already given. It's already marked vertically downwards. 300 newtons and 100 newtons. So step number two is also done. Step number three is to mark the reaction offered by the contact surfaces or to mark the normal reaction. Normal reaction will always be perpendicular to the surface. It will be directed towards the body and it will act exactly at the point of contact between the body and the surface. So you have 1, 2, and 3 contact surfaces here, and 1, 2, 3, and 4 contact points, out of which Q is the contact point between the two spheres. Now let us start marking the normal reaction. So this particular surface is in contact with the upper sphere, the lower surface is in contact with the lower sphere, and this vertical surface is in contact with the lower sphere. Let us start marking the normal reaction, which is step number 3. So normal reaction, let me consider point P. So normal reaction will always be perpendicular to the surface. Directed towards the body, and it will act exactly at the point of contact between body and the surface, which is P. So let me write it as N, normal reaction about P. normal reaction about P or just R reaction about P. Let me consider S now. Point S. Again, normal reaction should always be perpendicular to the surface, directed towards the body, and should act exactly the point of contact between body and the surface, and point of contact is S here. So let me write normal reaction. Let me consider this as normal reaction about S. Similarly, let me consider R. Again, normal reaction should always be perpendicular to the surface, directed towards the body, and should act exactly the point of contact between body and the surface, and point of contact is normal. Point of contact is R here. So let me indicate this as normal reaction about point R. Now, as we discussed in the previous problem, if two bodies are in contact with each other, both the bodies will offer reaction or normal reaction on one another. So lower sphere will offer a normal reaction on the upper sphere, and upper sphere will offer a reaction on the lower sphere. So lower sphere will offer a reaction towards the center of the upper sphere, and upper sphere offers a normal reaction towards the center of the lower sphere, or basically we have to. So lower sphere will offer a reaction towards the center of the upper sphere, and upper sphere will offer a reaction towards the center of lower sphere. Both are normal reactions. So this will be normal reaction about Q, and even this will be normal reaction about Q. Magnitude of both will be same, as we did this in the previous problem. Now, step number 4 is to mark the tension along the string. There are no strings given here in the problem, so you can eliminate step number 4 and you can directly go to step number 5. In step number 5, what do? We reproduce only the coordinates and forces systematically by bringing all the forces to the center. We reproduce only the coordinates and the forces. And we bring all the forces to the center and we draw it separately. And what you draw in step number 5 is the free body diagram. So this is the 5th step in drawing the free body diagram. So you reproduce only the coordinates. I will draw it here. You reproduce only the coordinates. You have 2 coordinates here. Only the coordinates and the forces systematically. Only the coordinates and the forces systematically. In order to do this, in order to go through this step number 5, to reproduce only the coordinates and forces, we need the inclination of all the forces, all the reactions. So self-weight, as you know, it moves vertically downwards. You can straight away mark self-weight, which is 100 Newton and 300. You can straight away mark self-weight. No issues in that. Now, let us go through NRP, normal reaction about the P. So it is horizontal, it has no inclination, so you can straight away mark NRP. Its original position will be in the positive x scale. Let us apply principle of transmissibility in order to bring everything to the center. Let me mark NRP here. Let this be NRP. We are concentrating on the upper sphere now. And we have to mark NRQ. Let us go through NRQ later. Now let us concentrate on the lower sphere. We have marked the self-weight. We can mark NRS. Let me mark NRS here. NRS. Its original position is in the negative y scale. I can apply principle of transmissibility and push it to the positive y scale. Let me consider NRR, normal reaction about R. Its original position is in the negative x scale. I can apply principle of transmissibility and I can draw it here in the positive x scale. Normal reaction about R. This is how it looks. So this is center A and this is center B. The center B, I will mark it, I will write it here. This is center B. Now the last force which is left out is NRQ. We did not mark NRQ here. The reason is we don't know this inclination. We should know this inclination, theta. We don't know this. This is theta, even this will be equal to theta. We don't know the inclination. Now, how to find the inclination is the question. In the previous case, when both the spheres were identical, you had a surface which was parallel to the line joining the center, and you could easily find this angle theta. But here it's not the case. You have to find the value of theta. In order to find the value of theta, let me extend this. And let this be right angle triangle. So this is A, B, and let me mark this particular point as, say, O. This particular point as O. Now this is the extension of this y-axis. Let me extend it till bottom. And this is the extension of this one. We don't know. So let us consider this right angle triangle ABO, right angle triangle ABO, to find theta, So what is the dimension of this now? We need the dimension of adjacent side as well as we need the dimension of the opposite side. We need these two dimensions. Now, or it's okay if you find the dimension of hypotenuse. Either of these three dimensions we need to find the value of theta. Now let us find the dimension of the adjacent side. In order to find the dimension of adjacent side, dimension, this particular dimension is 20. As you know, it is the radius of the lower sphere. This is 30. So what's the left out dimension? It will be 40. So this will be 40 mm. So we got the dimension of the adjacent side. Now it's easy to find the dimension of the hypotenuse. So this will be the radius of lower sphere. This is 20, and this will be the radius of the upper sphere. 30. So 20 plus 30, it will be 50. This dimension will be 50. Yeah. So we know that hypotenuse is 50 and the adjacent side is 40. So which operation can we use? We can use cos. So what is cos theta in this right angle triangle? Cos theta will be adjacent side by hypotenuse. Adjacent side is 40 by hypotenuse is 50. You'll get the value of theta as 36.86. So this theta is 36.86. Theta is 36.86. So now let me join the centers. In this way. So this will be NRQ, and even this will be NRQ. So this angle, as we found just now, is 36.86. So even this angle will be equal to 36.86. If this is 36.86, even this will be 36.86. If this is 36.86, even this will be 36.86. So this will be the free body diagram. This is the original position of NRQ. We have applied the principle of transmissibility and we have pushed the forces. So these are the two free body diagrams what we have. Two free body diagrams. This is the free body diagram concerned with the center A. This is the free body diagram concerned with center B. So when you have two free body diagrams, let me rub the question. When you have two free body diagrams, you are supposed to select that particular free body diagram with least number of unknowns. So which free body diagram has least number of unknowns here? Let me draw the free body diagram properly again. So this is NRQ, and this angle is 36.86. This is again NRQ. Angle is 36.86. Self weight is 300 newtons, and here self weight is 100 newtons. And this is NRR. This is NRS. And we have NRE. This is center B, this is center A. This is the free body diagram what we have. This is the free body diagram. I think we did not leave any of the forces. Now, so as you have two free body diagrams concerned with center A and free body diagram concerned with center B. So you will be selecting one of the free body diagrams here with the least number of unknowns. So let us try to find the number of unknowns as far as the lower free body diagram is concerned. NRQ 1, NRR 2, NRS 3 unknowns. Upper free body diagram, NRP 1 and NRQ 2. So this has least number of unknowns. So you have to select the free body diagram with least number of unknowns. So let me select the free body diagram with least number of unknowns, which is concerned with center B. Let me redraw the free body diagram of center B only. So this is 300 newtons. This is NRQ, and this is NRP. Center is B. So this angle is 36.86. Now let's just go through the free body diagram. Just go through the free body diagram. How many forces do we have? This is step number 2. Now we have drawn the free body diagram. We are done with step number 1 by drawing this. Step number 2 is to go through the free body diagram. Go through the free body diagram. If it has only 3 forces, you can straight away apply Lamin's theorem. If it has more than 3 forces, go with the conditions of equilibrium. How many forces are there in this totally? It's not about unknowns. Totally, we have 1, 2, 3 forces. So you can straight away apply Lamin's theorem. Let us apply Lamin's theorem. According to Lamin's theorem, NRP divided by sine of angle between the other two forces, NRQ and 300 newtons. Done. So the next one will be NRQ divided by sine of angle between NRP and 300, which is 90. Is 90 is equal to 300 divided by sine of angle between NRP and NRQ. This total angle is required, which is 143.14. Sine 143.14. So this is the application of Lamin's theorem. Here, these are the two unknowns, and this particular term is completely known. So equate these two as equation number 1 and equate these two as equation number 2 to find the value of NRP and NRQ. I'll not do this. You can try. Calculation remains the same. Calculation part remains same. This is all about the first free body diagram. And let us go through the second free body diagram now. Second free body diagram. It is the free body diagram concerned with this one. So when you draw the first free body diagram, you get the value of NRQ and NRP. So NRQ is common in the first free body diagram as well. So which is 500.1 here. NRQ is 500.1. You get this, you get the value of this when you apply Lamin's theorem. So when we draw the second free body diagram, it will be somewhat like this. The second free body diagram goes in this way. Self weight is 100 newtons. This is NRR. This is NRQ. We know the value of NRQ as 500.11. And this angle is also known, which is 36.86. And this is NRS. How many forces do we have? 1, 2, 3, and 4 forces. Totally 4 number of forces. So you cannot apply Lamin's theorem. When you cannot apply Lamin's theorem, you have to apply the conditions of equilibrium. Let us apply two conditions of equilibrium: summation of Fx equal to 0 and summation of Fy equal to 0. This is the first condition. Summation of Fx equal to 0. In order to apply the conditions of equilibrium, you have to resolve the force into their horizontal and vertical components. Let me resolve this particular force into its horizontal and vertical components. So the horizontal component of this force will be 500 cos 36.86, which is negative. It moves vertically horizontal to the left hand side, and this will be minus 500 sine 36.86. So let us apply the first condition of equilibrium, which is summation of. You cannot apply Lamin's theorem because you have totally 4 number of forces. The first condition is summation of Fx equal to 0, which is for minus 500 cos 36.86. This is the force, plus NRR, normal reaction about R, is equal to 0. So straight away get the value of NRR. Normal reaction about R will be 400.13. Just take it to the other side. Get the value of NRR. Apply the second condition. Second condition is summation of Fy equal to 0. So second condition is summation of Fy equal to 0. Check all the forces which moves in y direction. Minus 100 to minus 500 sine 36.86 plus nrs is equal to 0. By applying this, we'll get the value of nrs. Nrs will be around 400 newtons again. 400. Simple calculation. So this is how you are supposed to do. The only change is with respect to the angle what you find when you draw the free body diagram. Angle concerned with the point which joins the centers of two spheres. This is the only change what you have when you compare this particular problem with the previous problem. And then all other steps remain same. You just have two steps here. Remember this. Step number 1 is to draw the free body diagram, and step number 2, you'll be going through the free body diagram, or you'll be understanding the free body diagram. If it has 2 forces, 3 forces, you can straight away apply Lamin's theorem. If it has more than 3 forces, go with the conditions of equilibrium. As simple as that. Again, in step number 1, to draw the free body diagram, you have several sub-steps. First sub-step is to identify the center, draw the coordinates. Second sub-step is to mark the self-weight. Third sub-step is to mark the normal reaction offered by the surface. Fourth sub-step is, if it has a string, to mark the tension which moves away from the body. And in the fifth sub-step, you'll be reproducing only the coordinates with the forces by bringing all the forces to the center and systematically arranging it to draw the or to get the free body diagram. Once you get the free body diagram, you are done with step number 1 as far as problems of equilibrium are concerned. In step number 2, you'll be going through the free body diagram, what you have drawn. If it has 3 forces, apply Lamin's theorem. If it has more than 3 forces, go with the conditions of equilibrium. As simple as that. So go through all the problems. I've completed all the types now as far as spheres are concerned. We went through single sphere. We went through 2 identical spheres. We went through 2 non-identical spheres as well. So I have solved 3 example problems in the video. It's better if you go through all the problems from the notes. You have around 6 or 7 problems. Go through all the types. Thank you.